All right, I've had a lot of students asking for a review video for Algebra 2, Topic 5, so we're going to knock that one out now. On the screen, you have your first two questions. And instead of trying to do 234 to the fourth power and then taking the fourth root of that, I want to point out that if I take something to any power and then I take the root of the same power, or the root being the same as the power, I'm going to get the same number. So this answer is going to be 234. And if you want to see that working in action, let's do two examples. Here's the square root of 4. And let's do the third root. Sorry, this would be squared of 3 cubed. 4 squared is 16. We know that there's an understood 2 here for second root. And the square root of 16 puts me right back at what my base started as. Here, this is 3, 9, 27. And the third root of 27 is 3. So what happens here is this number and this number cancel. This number and this number cancel. And the reason it does that is because if we were to convert this into a rational exponent, this is my power, this is my root. This simplifies to 234 to the 1 over 1, which is just 234. On the second one here, I have no way for you for an exact answer other than to use a calculator, but we can use some common sense here. It's not called the sandwich theorem, but there's quite a few things in math that you call the sandwich theorem or the squeeze, where you try and see where something fits in between two other known values to make a determination of where they should be, or eventually pin them down to their exact value. And all I'm going to say here is the square root of 10.1. Well, I know that 3 squared is 9, and this is 10.1 is greater than 9, so it's going to be greater than 3. And then 4 squared is 16, and 10.1 is much less than 16. So then I can see by this inequality that my answer is going to be 3 point something. I just don't know what that something is yet. But when I pull up my calculator, I can take the square root of it, and I see I get 3.178. So let's put that in there. And then when this rounds, this is going to give me 3.2 to the nearest tenth. So that's your first two questions. All right, when we're given something like this where it says simplify the expression a to the 8th over b to the 12th, and we're taking the square root of that, I'm going to convert this every single time into a rational exponent. And that just means, remember, that we have the base is raised to the power over the root. This is my power. This is my power, right? It's exactly what we've been calling it, forever. And then this is my root. Obviously, there's no number here, so this is understood too. So if I convert that, I'm going to end up with a to the 8th power, so that's my numerator, over the second root, divided by b as my base, over, with 12 in my numerator, over 2. And then it's much easier to see that this is going to simplify to a to the 4th over b to the 6th. Do this for all of these problems. Convert them to an exponent, and you can solve them that much more quickly. All right, so this one wants us to multiply, and what we're doing basically is distributing, slightly different than what you're probably used to or what the standard convention is, where we put the multiplier on the left. But we're just going to take this square root of 3, multiply it through. So let's do that. If I take the square root of 3 and I pop it in here with this square root of 75, that's going to be the square root of 225. And then if I do this here, this is going to give me 2 times the square root of 36, and I'm subtracting those. This is going to be 2 times 6 minus 15. This is 12 minus 15, which gives us -3. And if you wonder how I got these 225s and stuff, This is back in Algebra 1 when you take two numbers, as long as they have the same root here, these are both understood twos. This is the same as 75 times 3 is just 75, 150, 225. All right, guys, this one's going to have a lot of work. I know if you had me for Algebra 1 or geometry, I told you I'll never make you rationalize the denominator. But in this case, to me, and what I'm thinking here is this is going to be much easier to go ahead and rationalize this denominator. Now, of course, if you guys have an easier way to do this, please share it with me. So to rationalize this denominator, I'm going to multiply by its conjugate here. So that's going to be the square root of m plus 1. I'm going to do that on both sides, so this is the same as multiplying by 1, so I'm not actually changing anything. When I FOIL this out, I'll end up with m times the square root of m plus m minus the square root of m minus 1 over, this is going to be the square root of n times the square root of m, leaving me with m, plus the square root of m minus the square root of m minus 1. What's nice about having done this is these now cancel, and I have a rational denominator. And then here, I'm going to rearrange this to see what I can get. Just put it in like terms, as in these two have like terms. So I'm going to rewrite this so that I have m square root of m minus the square root of m plus m minus 1. And the reason I'm doing that is I can see that I have a denominator now of m minus 1, and I'm starting to group my stuff into like terms where they can be turned into an m minus 1, which will allow me to cancel. Right here, the square root of m and the square root of m can be factored out. This is going to leave me with the square root of m. This will leave behind an m when I pull it out, minus 1, plus m minus 1. And all of this is over m minus 1. Now, my knee-jerk reaction here is, all right, I've done a lot. I've had to think this through quite a bit. And now I have two m minus 1s in the numerator, and I can cancel them out. But I have to pause there and see that I, in fact, can't do that because I still have a plus sign. So I'm going to bring this over here, but I'm going to simplify it. And what I'm going to do to simplify this is here, on this side of the plus sign, I have an m minus 1. On this side of the plus sign, I have an m minus 1. So I'm going to pull those out. That's going to leave me with m minus 1. And then that's just going to be my square root of m plus 1. And now if I think about that in reverse, if I distribute this in, I'm going to go back to the square root of m times m minus 1 plus m minus 1, which is exactly what I have. But what's nice here is I no longer have any operator here other than multiplication, and the opposite of multiplication is division. So these cancel, and I end up with m plus, or square root of m plus 1, and that is my answer choice C. All right, guys, I know this is multiple choice on your review, but we're going to do this without the multiple choice options, because when we can arrive at an answer and then verify it as one of the right options, we can feel so much better about it. So let's just start by rewriting this function. And then we're going to talk about translation. So I'm just going to draw a graph here. We're not going to graph this function. We're going to use a very simple case here to see how that simple case would behave and where the modifications to my graph would happen. And then we can move on and apply that down here in this more complicated example. So for this one, I'm just going to graph the point at 0, 0. And I'm going to move this point based on the directions here. So like here, it says translated left 2 units. So we're going to call this point A. And we're going to move it 1, 2 units. And then we need to move it up 1 unit. So this is where A prime is going to end up. And I can see here, I had a translation of -2, 1. Now remember, in my x coordinate, if I'm going to the left, that's a negative direction. But when it attaches itself to the x, we have to ask ourselves, x going to the left equals what? And this means we're going to have a positive 2 attached to the x. So this is going to end up being x plus 2. And then when we go up 1 unit, this is our y-intercept. And I know in Algebra 1, the y-intercept was always at the end. But here, that's fine. It's still shifting it up 2 units, and we need to shift it up 1 more. So this is going to give me a final answer of 3 plus the square root of x plus 2. And if we look at our options, that is option A. Again, if you go back to your geometry class and you think about your topic 3 rigid motion transformations, anything I can do to this point is going to be analogous to what I'm doing here to any of these points, right? So here on A at 0, 0 to A prime at negative 2, 1 would have that to the left and up 1 is going to happen exactly the same on every point on this function that we're being asked about. So if I can go back and simplify it by a point basis and then apply everything here, every one of those points has moved the same. We're not stretching and we're not shrinking or compressing this graph at all. So this is a rigid motion, and we're able to go back and do it this way, making everything so much easier for us. All right, the question doesn't get much easier than this, especially if you understand what's actually going on here when we find the inverse of a function. So our original function has a domain where x must be greater than or equal to negative 2, and a range where y must be less than or equal to 1. If I were to find the inverse of that, all I have to do then is swap my x's and my y's. Domain is in reference to the x, the range is in reference to the y. So I'm going to end up with x is less than or equal to 1, right? That was my range value before, and I swapped it. And then my range is y is greater than or equal to negative 2. All we're doing is swapping the inputs and the outputs. All right, for this one, they're testing your understanding of the actual number theory, or the types of numbers that we have. So I'm going to just break this down here to the numbers in which we all pretty much know versus what we've just learned. So we start with the real numbers. And the real numbers include, let's just go from the simplistic, the natural numbers. Your counting numbers, right? Can you count it on your fingers and keep going? Start at 1, keep going. The whole numbers. That's the natural numbers plus the number 0. Took a while for us to figure that out as humans. We have the rationals. That's kind of what we've been doing here with our exponents. A over B is terminating, repeating our whole, or an integer. We have our integers. We have our irrationals. And irrationals and imaginary or complex in the beginning are the easiest ones to mix up. The irrationals are numbers like pi, right? They never end, they never repeat, they keep going. Euler's number, etc. What else do we have? Natural, whole, rational, integer, irrational. Anyways. And then outside of those real numbers, we also have something called the complex or imaginary numbers. And that's when I take the square root of a negative number. I don't really have a way to do that, but I do end up with that nice little I tacked on the end. And there's more sets that are out here, but these are the ones that you guys should be more than familiar with. Everything in the left bubble, the real number, you should have covered in depth and exhaustively in Algebra 1. And then in geometry, when you got there, we basically worked in the whole numbers because we never went negative, because we were mostly talking about real world links. Now you're in Algebra 2, and at the very end of Algebra 1, you should have seen complex numbers. And that's just something we can't graph on a real number line. or a real plane. Let's be more precise. So what I have to do here is decide which one of these circles, or which one of these circles do these numbers belong in? Well, on the left, if I take the square root of 115, not going to be imaginary because this is a positive number under an even radical, but it is going to be irrational. And because it's irrational, let me make my pen just slightly larger. Because it's irrational, it's still a real number. So it wants to know, is it real? Well, yep, this is good to go. Irrational numbers still belong to the real numbers. Square root of 0 is 0, and 0 is introduced in the whole numbers. It also belongs in the integers. So we are good to say this belongs in the set of real numbers. Next, we have the negative cube root of 16. And we're going to feel right away that that's not going to be real, most likely, but we have to pay attention to this right here. This is asking for the third root of a negative square root of 16. Now, there's a lot going on here, so let's break it down to make sure we see why this is still a real number. If I look at this first, because if I follow the order of operations, I have to start here. This negative is outside of my even root. So I'm going to take the square root of this first, and that's going to be 4. This negative stays, and now I have the third root of negative 4. But remember, if it's if it's an odd root, negatives are allowed. So this is just going to be whatever number we have to, multiply by itself 3 times to get to negative 4, which is best represented as this. Now, this is a real number. And even though we can't do this, what if I were to give you this instead? Well, we know here this can be 2 and 4, 2 and 2. I have a third root, so I bring this out in groups of 3. And then I just bring the negative out. Oops, sorry, that's a negative 2. I have 3 2's, so the 2 comes out. Keep the negative, and then I'm going to ask myself, does this value cubed give me negative 8? Negative 2 times negative 2 times negative 2. The first time I do this, I get 4 times negative 2, and that leaves me with negative 8. So then if I were to take the cube root of that, I'd end up back at negative 2. So this one is actually safe. Now the question becomes, what do we do with this guy right here? Well, let's start clearing some of this off so that we can see what we're going to do with this. Let's make this larger than 100%. Let's try and make heads or tails of this one. There's a lot going on here. I don't like that color. Let's go with this one. So already I see I have an even root. When I see I have an even root, I have to be cognizant. I have to keep in mind that I could end up with a complex number. So when the root is even, pay attention for complex answers. So I already know that. Now, the question becomes, is 1 minus the square root of 2 positive or negative? If it's positive, I'm golden, right? A square root of a positive number is always real. If it's negative, I don't have a real number because I have to pull that negative out by making it I, because I squared gives me back that negative, and it's complex. So on my calculator, I'm going to do 1 minus the square root of 2. And this value right here is approximately negative 0.41, right? Now, my question was, is this positive or negative? And you can see here that it's negative. So what I'm really asking myself is, what is the fourth root of approximately negative 0.41? And I know if I have a negative there, this is going to be complex. So I'm just going to write complex here. And therefore, A, B, and C are all real numbers. A and B, very nice, easy, and to the point. C, you have to keep in mind that this negative is not under the even radical. So it's still going to be a real solution here. And it's okay to have an odd root with a negative under the radical. All right, guys, welcome back to the second to last lesson of geometry for, your geometry course. So now, a lot of you that are watching this year ended up doing geometry quarter 4 online, so you may not have had a chance to do this one in depth. This is a pretty straightforward and easy one. It gives you the equation for volume, and it wants you to find the radius to the nearest tenth of a meter when the volume is equal to 10 meters cubed. Now, it's good that they do this for us. As you can see here, we have two potential variables. We can either be solving for V if we know R, or if we know V, we're able to solve for R. So we're going to do our substitution in right here. And this is going to give us 10 is equal to 4/3 pi R cubed. And it does want us to solve for the radius. So to do that, I'm going to slowly start chipping away to get my radius by itself. And my first step, as always, is to multiply by this reciprocal. This is going to give me 30/4 is equal to pi R cubed. Now I'm going to divide both sides by pi. And if I wanted to do that, I'm going to go ahead and punch in the calculator 30 divided by 4, and then divide that by pi. I get 2.387. No surprise there that it's an irrational number. These will cancel, and I'm left with R cubed is equal to this. Do not clear this out of your calculator. Do not round to the final step. Make sure your display is showing more than 2.387 because you did do 30 divided by 4 divided by pi to get that number. Your calculator is storing more digits than it can show you by a large amount. So what I'm going to do now, while I'm still seeing the 2.3873214 on my screen plus more, now I'm going to take the third root, and that's going to tell me that R is approximately 1.336504 and then more. But it says to the nearest tenth. So if I look here, R is approximately 1.3. Now don't forget my units, meters cubed. All right, guys, this one's pretty easy if you know the trick to it. To show you the trick to it, I want to make sure we understand how to do something like simplifying this, because knowing this right here is going to do everything we need to know. It's going to cover every idea that we need to multiply by this in the most simplistic way possible to do it. Here, if I were to simplify this, I know the smallest prime I can divide that by is 2. And since you guys are in Algebra 2 now, I'm not going to waste your time breaking this down into groups of 2 and doing all that. This is just 6 times 6. This radical has the understood 2 there. So bring the 2 6's out, leave the 2 behind. Now, if I wanted to check it, the way I do that is, remember how I had to bring this out in groups of 2? To put this in, I have to make it back into groups of 2. So this is really the same as 2 times 6 times 6. This will give me 18 times 6, which is 72, right? So to move it out, I need to take the square root of this number is really what's happening. This is why we tell you in groups of 2. It's just the square root of 36, and it leaves 6. Here, to put it back in, I have to square anything going inside of it. So now that we kind of know that, if we didn't already, how much easier this problem is going to actually be to solve. Let's go to a darker color. My monitor is acting funny today, so it's kind of hard see some of these. Let's first change this from a proper to an improper fraction. 2 times 1 is 2, plus 1 is 3. And we're going to multiply that by 9 times 1 is 9. And here we have plus 7, so 16 over 9. Now, I want to move 3 halves inside, so I'm going to go ahead and rewrite my 16 over 9. Now, remember, going inside, I square everything so that if I want to pull it back out, I can have a pair of 3 halves. This is going to give me 9/4. So all I have to do now is multiply these together. 16 times 9 is just going to be 160 minus 16, so that's 144. And 9 times 4 is 36. Now, I can take the square root of both of these right now, or I could just simplify this. Whichever way you want to do it is right, and we'll go ahead and do it both ways. Let's do the square root way first. This is going to leave me with 12 over 6, which is 2, or 144 divided by 36 is 4, and that gives me 2. So there's 2 ways to do this. There's actually a lot more. We can make it as complicated as we want, but we can see both times. Let's make this 2 a little bit nicer. We get an answer of 2, and that is our answer for the question. All right, if the answer to this one, which of the following is a decreasing function, is not intuitive to you, right? If you can't just look at this and see which one it's going to be, what I recommend is picking a value for x and testing it, right? Multiple values. Now, here, these are all, well, these 3 all have an even root. So to make this way work, I have to make sure that I'm not, outside of my domain restrictions. So here, x must be greater than 2. So when I pick the t-chart for this one, my x's are all going to have to be greater than 2 when I choose my y. Sorry, greater than or equal to. And now if I put 2 in, I get 2 minus 2, which is 0. Square root of 0 is 0. Now I'm not going to pick 3, 4, 5 going down the way. What I'm going to do is recognize that this is a square root. So I'm going to pick my next perfect square, which is just 1, but that's outside of my domain restriction. Sorry, greater than my x. That's 3 doesn't have a perfect square. 4 does. So I'm going to say 4 plus what number? Plus 2 gives me what number? That's 6. So my next choice is going to be 6 to see if this is decreasing or increasing. 6 minus 2 is 4, which gives me back an answer of 2. Right now I have evidence that this is increasing, but as we know from geometry, we never trust just 2 data points. So now I can see that last time I chose 4 and I plugged in 6, my next perfect square is 9, and 9 plus 2 is 11. So if I plug 11 in here, I get 9, which gives me a value of 3. So this is becoming more and more evident that this is going to be increasing. I'm going to do one more just for the sake of making sure we do it right. Here, I'm going to want to get 16 under this radical, so I'm going to put 18 in for x. That's going to be back 4. Now, you might say, well, how do we know we're not skipping anything? Well, look how my output values are increasing here. 2, 3, 4. So that means if I were to put in 5, I would be able to know that this is going to give me back 27. All right. Plug it in. 27 minus 2. Take the square root is 5. So I'm not missing anything here. And this is definitely increasing. All right. Now, B, they're throwing this negative sign out front because what they want you to do is think, oh, automatically decreasing, right? Well, let's see if that's the case. Here, though, we have a different situation. We have 2 minus x. So in this case, x must be less than or equal to 2. Right? Because if I put in 3, I'm now in the complex plane, and already we're not making any judgments on that. So for x must be less than or equal to 2, our first option is let's go right up and just touch the domain. This is going to be 2. When I have 2 here, this is 2 minus 2, which is 0, and that gives me negative 0, but negatives don't impact 0, so I have an output of 0. Next up, and here's where it gets fun, I'm going to actually choose negative 2. And here's why. What is 2 minus negative 2? Well, that's a positive 4, and that gives me, that gives me 4, which is just square root negative 2. Up next, we're going to put in negative 7, which is going to give me 9, which is going to give me negative 3. Up next, we're going to have negative 14. Notice these are always off by, they're always 2 away from some perfect square. This is going to result in negative 4. But if I were to graph this, when x is 2, y is 0. Now here's where it gets funny. When x is negative 2, this is negative 2. When it's negative 7, it's negative 3. If I look at my graph, that's still increasing. So this is not a decreasing function. Everything in us would say this is definitely decreasing. We started with a negative out front. The numbers, our outputs are getting smaller, but what's happening is we're also getting smaller as we go further along our x. Like here's negative 14. We're going to be all the way down at negative 4. And you can see now, because we always read graphs left to right, this one is still increasing. So we clean up a lot of this mess. Keep that. This one's still increasing. Now, let's look at, first off, a better color. C. Do an XY table for that. And you may be confused as to why I didn't do it here. This is our standard graph. X is increasing, Y is increasing. X is decreasing here, as well as decreasing on Y. Double decreasing means that we're actually looking at a positive trend. It's kind of like the idea of 2 negatives make a positive. So what we want here is one graph, or input or output to have opposite directions. One needs to be decreasing while one's increasing, and that's how we get a decreasing function. So for C, I have 2 minus the square root of x. Now this one's the nicest to us. We can just put in perfect squares for our input, and then we can get our trend out of it from there. If I plug in 0, I get 2 minus 0, which is still 2. If I plug in 4, I get 2 minus 2, which is 0. If I plug in 3, I get 2 minus 3, which is negative 1. And here I have 4, so that's negative 2. Now look, this is exactly what I just described. My x's are increasing while my y's are decreasing. And if I graph that, here's 0, 2. Here's 4, 0. 9, negative 1. I can see my graph is going to be decreasing. So it says which of the following? That's going to be that one. Now, of course, I'm not going to say let's just move on to the next question, because I want to feel confident that what I've done is actually correct. So let's go ahead and throw in the cube root of x just so we can compare it and make sure that we are good to go. So for D, I'll have my XY table. And here I'm just going to pick for my inputs perfect cubes. 0 is going to spit back 0. 8 is going to give me 2. 27 is going to give me 3. This is increasing along x. This is increasing along y. And that leaves c as my only decreasing function. All right, for those of you who had geometry with me, we finally get to revisit this and what you're going to use it more commonly in across all of your math classes. This is no longer a composition of rigid motions. This is actually taking two functions and seeing how they fit inside of each other. So for this one, I have f composed of g, which means I put g into f. So I'm going to rewrite f first. That's just square root. And then I have an x there. So that means whatever I have for g is going in here. And then it says, what's the domain? So all x's must be, and then we have to figure that out. Well, this is the radical function, right? We know that to stay in the real numbers, which is what we're considering in the domain, it's not asking us to graph in the complex plane, that this x minus 5 must be greater than or equal to 0 for this to be defined along the domain. So I can just solve for x by adding 5 to both sides. And I know that x must be greater than or equal to 5. And if I want to test it, let's put in 4 here. This is going to give me 1 over 4 minus 5. This is going to give me 1 over negative 1, which just simplifies to the square root of negative 1. And this is no real solution. And then if I plug in 5, we have a problem. And this is why we always check our work. What do we get here? This is undefined. Whoa, pressed a little bit too far over. Where in the world did I go? All right. So we need to go back here and we need to edit our answer. We can't have that equals to as we're showing because we get an undefined result. What a surprise. Now, let's test it again. X must be greater than or equal to 5. So let's pick a really small 5 just to help settle ourselves into this answer. And let's go with this color. Let's say that x is equal to 5.0001. This is going to be 1 over 5.00001 minus 5. And that leaves us with 1 over 0.00001. And that is positive. And this domain is good for any positive results. So as long as I have a number greater than 5, I can feel confident in my answer. All right, guys, let's knock out our first inverse equation. Remember here, this a of x is just another way to write your output variable. So I'm going to start by switching back to our y. And the reason why is going to be very obvious in just a second. Whenever I want to find the inverse of a function, I'm going to rewrite this as the output variable equals 1 over what I was given. Or sorry, the output variable is equal to whatever I was given. Then my next step is going to be every time swap my variables and then resolve for the output. And that will give me the inverse. So now I'm going to have x is equal to, I tried to find the same color that I started with. There it is. 1 over y minus 1. Do you see how they switched? It's literally wherever I saw an x, I made it a y. Wherever I saw a y, I made it an x. And then we go ahead and just solve for y now. So to do that, I'm always going to start, no matter what, even if there's a faster way, and there probably is, start by multiplying by whatever is in my denominator. This is going to leave me with x times y minus 1 is equal to 1 because these will cancel when I distribute through. Now I'm going to distribute my x in. is going to give me x, y minus x is equal to 1. Let's go ahead and get our... Why isn't this working? Well, that's a heck of a meteor shot there. Let's get our x over. This is going to leave me with xy is equal to 1 plus x. And then to isolate this, I'm just going to divide by x. And this leaves me with y is equal to 1 plus x over x. And let's see if that's one of our answer options. Of course, I'm going to want to change this back to my function notation. This should just tell me the inverse of a of x is equal to 1 plus x over x. And if you're looking at this, of course, they put the variable first. This is the same because I can rearrange addition. And that is option B. So the best thing I can tell you to do when it's asking you to find the inverse, rewrite it, not in function notation, but input-output variables. Swap your input and output variables, and then solve again for your output. All right, this is just a composition of functions without it being labeled a composition of functions. It says evaluate the expression x squared minus 4x plus 1 when x is equal to 2 plus the square root of 3. There is a couple ways we can do this. We can see if we can factor it down, and that would make it easier in some cases, but let's just go straight for it because I'm not sure exactly how you guys are used to seeing it. So anywhere I see an x, I'm going to plug in 2 plus the square root of 3. So this is 2 plus the square root of 3 squared minus 4 times 2 plus the square root of 3 plus 1. The expansion on this is just a squared plus 2ab plus b squared. This is not 4 plus 3. You have to have this middle term. This is what comes out of FOILing. So a is 2, so that's 4, plus 2 times a times b plus b squared. And that will be our first part. Let's go ahead and distribute my 4 in. So this is going to be minus 8 minus 4 square root of 3 plus 1. Now I have 4 plus 2 times 2 is 4 times the square root of 3. This is already looking really nice for us. Square root of 3 squared. It's exactly like we said in the very first problem. Taking the square root and squaring something just gives me the base. Minus 8 minus 4 square root of 3 plus 1. Let's see what like terms we can start eliminating or combining. Positive 4 square root of 3 will cancel with negative 4 square root of 3. 4 plus 3 plus 1 is 8. And I know I have a minus 8 there, but I want to make sure you guys see what I'm doing. So I get an answer of 0. That's a lot of work just to get 0, but let's see if it's an answer option. Yeah, it is. It's actually answer C. And that's how that one goes. All right, guys, don't overthink this one. Don't try and find a expression or a polynomial or something that's going to generate these numbers. This question is asking if you understand that f of x and the inverse have a relationship that will always hold true. You can drive yourself crazy trying to solve for this. Remember, this is my x, this is my y for the given f of x. What we want to do then is look at this table of f inverse of x. It stays the same. The only thing that's changed is now instead of f of x, I have the inverse of f of x. And when f of inverse x is 3, my answer is 2. Now we could try and find ways to solve this and then find the inverse of that equation, but you're going to go crazy and you've got 90 minutes to finish this. So just keep it simple and make sure we are applying the rules that we've learned in this topic. All right, guys, so let's look at this one. We have if f of x is equal to 1 minus the square root of x, which of the following are true? Select all that apply. I'm going to start here. This is just our inverse identity. This is like saying that x plus 0 is equal to x for addition. Adding 0 is the identity where you keep the number the same. If I have a function of x and I find its inverse and then I compose them, I will always get back my x value. This one is asking us to find the inverse, so let's do that. I'm going to rewrite our original as y equals 1 minus the square root of x. And then I'm going to swap my variables. So I'm still going to keep the equals, the 1, the minus, and the square root. But my y is going to go here, and my x is going to go here. And now I need to solve for my y. So what I'm going to do is I'm going to go ahead and move the y over and then move the x over. This is going to give me the square root of y, because I add that on both sides, is equal to 1 minus x. And then I'm going to square that. I get 1 minus x squared. So is 1 minus x squared equal to x minus 1 squared? Well, let's put it to the test. Two t-charts. We have 0, 1, 2, 3. Here I have 0, 1, 2, 3. If I plug in 0, I get back 1. If I plug in 1, I get back 0. If I plug in 2, I get back 1. If I plug in 3, I get back 4. Now, of course, this is going to be 1 minus 3, so that's negative 2, and then 2 squared is 4. Here, if I plug in 0, I get negative 1. Square that, it's 1. If I plug in 1, I get 1 minus 1 is 0. If I plug in 2, I get negative 1, which gives me back 1. And here I get 3 minus 1 is 2, so that gives me back 4. And I can see that these are generating the same values. And then it just says f of negative 1 is equal to, or f of negative 1 when I plug in 0 is equal to 1. Well, I already know that that's true. And when I plug in 1, I don't get back 4, so that's not true. So this is a 3 out of 4 being the right answer for this. All right, for our next one, we have this equation, x minus 7 is equal to the square root of x minus 5. This one's pretty straightforward. We're going to square both sides to get rid of our radical. And give me x minus 7 squared is equal to x minus 5. X minus 7 squared, we're still going to stick with this a squared minus 2ab plus b squared. To solve this, this is going to be a squared minus 2 times 7 times x, and then the plus b squared is plus 49 is equal to x minus 5. I apologize, I switched my b and my a, but because we can swap multiplication, it is still going to give us the right answer. I just got distracted because my phone started ringing and I wanted to silence it. Here I'm going to end up with x squared minus 14x plus 49 is equal to x minus 5. Go ahead and subtract x from both sides. Add 5 to both sides. And we're left with this right here. And back to what you guys do pretty much all year before this in the class. How do we find out what the zeros or roots of this are? Well, what two numbers multiply to 54 add up to negative 15? 54 can be broken down, in my mind, to 9 times 6. Those two are not going to add up to negative 15, so I'm going to make these negative 9, negative 6. And that's going to leave me with x minus 9 times x minus 6 is equal to 0. And then I can break these guys apart to find my two roots. This is x minus 9 is equal to 0. This is x minus 6 is equal to 0. And this implies that x would be equal to 9. And this implies x would be equal to 6. Do not put your answers in yet, though, because we have to check for extraneous solutions. That is, do these answers both make sense in context of our original problem? So I'm going to come back up here, get a new color going, and I'm going to plug in. I have to test it both here. So it's going to be 6 minus 7 is equal to the square root of x minus 5. This is going to give me negative 1 is equal to the square root of x minus 5. There is no way that I'm going to get a real number solution that's negative from this, right? X minus 5 is never going to be equal to negative 1 in the real number system. It's not asking for, are there complex solutions? It's asking for real number solutions. So we're going to say that's an extraneous solution. It doesn't work. Mathematically, it works. But in the real world, I can't take the square root of x minus 5 and have that equal negative 1 without complex solutions. Now let's show you what it would look like when it would work. This one's a little bit easier to do in your head. Here, I'm going to have 9 minus 7 is equal to the square root of x minus 5. This is just going to tell me that 2 is equal to the square root of x minus 5. And that is 2. If I plug in 9 here, that's going to give me 9 minus 5, and that's 4, and the square root of 4 is 2. This is going to be my answer. This is good. And this one, so I don't have a red, do I? This one does not work because it can't produce a negative 1 when I have the square root of x minus 5. All right, hate to say it again, but let's not drive ourselves crazy trying to just plug and chug x's here until something works out for us. We got one thing going for us that will really help. That's right here. We have these two exponents. We have to think about, what does that actually mean? What does that look like if we were to convert it over to radical form? And I think it's much easier to see in radical form, but as you get used to this, you won't really have to be converting them to radical form. You'll recognize that the denominators are the same, and that means you can do something here. But let's go ahead and turn this into, remember, this is my power for my base, and this is my root, and the same applies over here for the 1/3. So this is the same as the third root of x minus 1 squared. And that's equal to the third root of x plus 5. And when I have that, it becomes really evident that my next step is to just cube both sides here. And then these will, the cube root of something cubed cancels the cube root for both of these. And I'm left with something much easier to work with. I have x minus 1 squared is equal to x plus 5. Now all I have to do is expand and solve. X squared, x minus 1 all squared, same thing we just did on the last problem. That's x squared minus 2x plus 1 is equal to x plus 5. Move all of this over, I'm going to end up with x squared minus 3x minus 4 is equal to 0. And my question becomes, what two numbers multiply to negative 4 but add up to negative 3? Well, that's going to be negative 4 times positive 1. Negative 4 times 1 gives me that negative 4. And then when I distribute, I'm going to have negative 4x plus x to get negative 3x. And then I can come back and set these both independently equal to 0. Because once one of these equals 0, the whole left-hand side is 0. And then this implies that x is equal to 4 or negative 1. And the nice thing about this, when we go to check for extraneous solutions, because these are third roots, or our root is odd, we do not have to consider complex solutions. Right? Odd roots can go, that negative 1 can go in for the third root. It's just going to be negative 1. Now, do we want to check if this is true? Well, if I were to ignore my blue lines here, if I plug in 4, that's 4 minus 3 is 3. Squared is 9. And the third root of 9 is Who knows? Off the top of their head. Who needs to know, right? Because here 4 plus 5 is 9, and that gives me the third root of 9 again. Obviously, the third root of 9 is equal to the third root of 9, even if I don't have a calculator to compare those decimals. Even though you can't actually trust a calculator because you can't see all the digits. If I plug in -1 here, I get -1 minus 1 is -2. That squared is 4, and that's the third root of 4. And here, again, I have the third root of 4. Doesn't matter what they are on the calculator. I know that the third root of 4 is equal to the third root of 4 all the time. That's how we knock out this one. All right, for that previous problem, I was recording and well, I thought I was recording, but I wasn't. So I just put a picture up. You can pause on it and watch it or review it to see the steps. For this one, this is our final one. It says, what is the least value of x such that the fourth root of x to the fourth is equal to x? And then you have the options. There is no least value of x. X is equal to -1, x is equal to 0, x is equal to 1. Well, since this is 4 and 4 is even, we can't put a negative number underneath that radical, which means that there has to be a least value. And then we just have to decide, is it now x equals 0 or x equals 1? Well, since 0 is less than 1, if this works, then we are good to go with that as our answer. Well, 0 to the fourth is 0, and the fourth root of 0 is 0. So this is our answer.